Okay, so this is 7.2 part 1, and the topic is inverse Laplace transforms. So the purpose of inverse Laplace transform is to undo a Laplace transform. Okay, so our definition of Laplace transform is that if you're given the Laplace of lowercase f of t, you get capital F of s. And then we can take pretty much the Laplace inverse of both sides. And when you take the Laplace inverse of capital F of s, it undoes this one, and you get lowercase f. So this also has the linear property. So again, when you take the Laplace inverse of a capital, you get the lowercase in terms of t, and same with that one. And of course, since it's linear, the a comes out, and the plus can be written as two different ones. So just looking at a table, so we proved that last time. So we take the Laplace inverse of both sides, and you get 1 equals the Laplace inverse of 1 over s. By the way, these two, this is actually a case of the exponential. If we have the Laplace inverse of 1 over s, that's equal to the Laplace inverse of 1 over s minus 0, which that means our a is 0. And so that's e to the 0t, which is 1, which we could have up there. So a couple tips. You want to know your transforms. Basically, we want to see the tables. We want to look at the denominator and build the numerator. So let's look at some examples. So this one uses this, and so we basically have an n plus 1, which is our 7, so we need a 6 factorial on the top. So if we need a 6 factorial on the top, we've got to put one on the bottom. And well, because it's linear, we can factor out the one we don't need, which is 1 over 6 factorial, which is n factorial, which is our 6. And we'll just leave that like that since 6 factorial is so big. So what we want to do is take this 7, keep it separate, and then we want the square root, since there's no s on top, we want the square root of 15 on top. Put it on the top and the bottom. And then you pull out your pull this out, and pretty soon we won't have to do it in the spinny steps, which is 7 over, and this is sine of square root of 15 times t. So basically we're looking for the inverse of capital F is lowercase in terms of t. And before we do that, we can do this intermediate step, but this isn't necessary. This is 3 times 1 over s minus 1 over s minus 2. Bring that 5, and that's 1 over s plus 3. So we can see it's 3, the inverse. And if we wanted to, we can even take the Laplace inverse of both sides. So we take the Laplace inverse and so our final answer is the Laplace inverse of 1 over s is 1. This is e to the 2t. And that's actually minus, it's the opposite. And that's our final answer. And we don't need that one really. Just 3. So we can pull out that 2 for sure. And we don't want that 3 in front of their s. So I'm also going to pull out a 3 here. And then we can also pull out that 3 in the denominator. And that's what we get. So we can break this up with a plus right here. Of course, it's keep the same denominator. It's going backwards of adding fractions. And then bring out the constants, the 2 and the 5. Except this one, we're going to want to build. We bring out that 5. We want the square root of 9, which is 3. It goes on the top there. It also goes on the bottom there. So if it goes on the top there, the square root of 9 is 3. You got to put it there on the bottom, but we can pull it out. And that will be 2 cosine. It's the square root of 3t. Plus 5/3, and that one is the sine of 3t. Final answer. This one we were able to just split up because we already had our denominator that was on our list of Laplace inverse transforms, but this one's not on our list. So we will have to use partial fractions. We basically want to take s plus 3 and we'll factor this denominator. And we want to find these constants so that it breaks up like that. Once those are constants, we'll be able to find the Laplace transform pretty easily. So I'm going to actually go over 2 methods that you've probably seen them both already, but just to remind you, it's probably been a while. So the first thing we need to do for both methods is to clear your fraction. do not know where I got plus 3. And we get s plus 3 plus bs. So our first method is we want to equate coefficients. So basically, whatever's in front of the s, so 1 is in front of the s, 1 is equal to a plus b. And then my constant has to equal to my constant. So this one looks like it's the one I want to start with. And then I plug that in there. Okay, and real quick, the second method's actually a little faster sometimes. Not all, you can't always do the second method though. And you still have to clear your fractions, so we will be starting here actually. Actually here. So you clear your fraction. It's pretty simple to see how to clear your fraction. You get s plus 3. And over here, the s cancels. You get a times s minus 4. And the s minus 4 cancels there, so you get the bs. So the second method is we're going to set something that clears away, zeros that a out. S equals 4. Again, it zeros the a out. So we get, plugging that in there, 4 plus 3 equals, again, a 4 minus 4, that's 0. bs, that's the purpose. So we get 7 equals to b. Oops, and we got to plug in s equals 4, like I said. Plus 4b. b equals 7/4, which is the same thing that we got up there. And the last thing, the 0, we'll zero that one out. So we get 3 equals a. Okay, so we got the same answer. So that's what we want. So we wanted the Laplace. So this becomes a is minus 3/4 times 1 over s. b is 7/4 times 1 over s minus 4. That's what this becomes inside. This is equal to that. So it's minus 3/4 Laplace. That's just 1, remember? And that's e to the 4t. About a third power there. So again, we're going to have to do the same thing. Factor that s out. And that is an irreducible quadratic. So if you remember, it's a over s, my linear, plus b s plus c. You got to use s, the variable on the bottom. And so we want to clear this fraction. We're going to equate coefficients because we won't be able to zero that out. So we can actually see here that there's no s squared term on the left. So a plus b is equal to 0. Our s term, 4 is equal to c. And my constant, 3 equals 9a. And for S, 4 is equal to C, the coefficients are equal. So we got 4 equals C, divide by 9, 1/3, minus 1/3. So Laplace inverse. So this is just equal to this, plugging in A, B, and C. So this is equal to A. A is 1/3 times the Laplace inverse of 1 over S. So just so you know, we are going to go one step further. I might as well just do it up here. That's A over S plus BS over S squared plus 9 plus C over S squared plus 9. Okay, so this gets broken up into 2. So this is equal to the A is the, so this is the Laplace inverse. The A is the 1/3 times 1 over S, plus the B is the minus 1/3 times the S over S squared plus 9, and then the C plus the 4 times the 1 over S squared plus 9. But we know we're going to need the times 3 on the top, so we times the 3 on the bottom because of that 9 that was there. And that parentheses, and then this way we can see, I'm just going to factor out this, this, and this. It's 1/3 Laplace inverse 1 over S minus 1/3 Laplace inverse M. That's 1. That is cosine of 3t. And that's sine of 3t. And that's our answer. And that's the end of this video. We'll have a part 2 where we'll talk about the Laplace transforms of derivatives.